Here I will explain first order high pass Butterworth filter using op-amp. Here R1 and RF are the two resistances which are used to determine the gain of the op-amp is in non-inverting configuration. Therefore, gain of the op-amp AF is equal to 1 plus RF by R1. Next, filter circuit consists of C and R elements. This is the description of first order high pass Butterworth filter circuit. Next, frequency response. Voltage gain is represented by A. Magnitude of that voltage gain is mod A. F less than FL in the range. Here F is equal to FL. Here F greater than FL. In F less than FL, the voltage gain of that filter circuit increases at the rate of 20 dB per decade. Slope is plus 20 dB per decade. At F equal to FL, voltage gain mod A is equal to magnitude of that voltage gain, that is mod A is equal to 0.707 AF. At F greater than FL, that is pass band in case of high pass filter, the gain is constant, that is AF. Next, coming to the magnitude of the transfer function which is given by this one is mod A is equal to output voltage by input voltage. This is output voltage V0, input voltage is Vin. Mod V0 by Vin is equal to AF into F by FL by square root of 1 plus F by FL whole square. In the coming session, I will derive this expression. AF is equal to 1 plus RF by R1 because op-amp is in non-inverting amplifier configuration. F by FL. Here common term is F by FL. FL by F whole square plus 1. This one is that is equal to 1 plus RF by R1 is AF as usual by square root of 1 plus FL by F whole square. In the frequency response curve, at low frequencies, that means F less than FL, V0 by Vin, mod V0 by Vin less than AF. Less than AF. That means here FL low, FL is high, the gain is increases like that at low frequencies. This is at low frequencies. That is the stop band. Stop band. At F equal to FL, therefore F equal to FL means mod A is equal to AF by square root of 1 plus FL and F are equal, therefore 1 square, that is equal to 1 AF by root at F equal to FL. At F greater than FL, this quantity is neglected because square term. Suppose FL is 1H, F is 4H, 1 by 4, that is 0.25. 0.25 whole square, low value. Compared to 1, that value is very low. Therefore, gain mod A is approximately equal to AF. In that region, mod A is approximately equal to AF when F is greater than FL. At F equal to FL, voltage gain mod A is equal to AF by root 2. At F less than FL, the gain increases at the rate of 20 dB per decade. Slope is plus 20 dB per decade. Coming to The circuit acts as high pass filter with passband gain as AF. This one is here. This is the passband. Passband gain is AF, constant one. This is mod A. For the frequencies F less than FL, the gain increases till at F equal to FL. This is the frequency. The gain is increases at F equal to FL at the rate of 20 dB per decade. Hence, the slope of the frequency response in this is the stop band. In the stop band, plus 20 dB per. The slope of the frequency response in the stop band is plus 20 dB per decade for first order high pass filter. Coming to this one, all high pass filter is basically a low pass filter circuit with positions of R and C interchanged. The design steps and the frequency scaling method discussed earlier for low pass filter is equally applicable to first order high pass Butterworth filter. Already explained scaling in scaling method in the last video. Next, analysis of first order. Analysis of first order Butterworth high pass filter. Butterworth high pass filter. Consider op-amp configuration. This one is op-amp configuration. This one is capacitance, resistance, or generally we use watt. This one is Vin. This one is capacitance. The voltage at point A is VA plus here minus V naught. This one is R1. This one is RF. This is the filter circuit. Filter circuit consists of C and R elements. Here B voltage at B is VB. According to virtual ground concept, according to virtual ground concept, virtual ground concept, difference between these two is VID. VID is equal to 0. VID means VA minus VB is equal to 0. VA is equal to VB. VA is equal to VB. This is the actual circuit. VA is equal to VB because VID is equal to 0. Differential voltage between these two terminals is equal to 0. Apply nodal analysis at point B. Point B, the node voltage at point B is VB. The node voltage at point B is VB. At point B is VB. Apply nodal analysis at point B. That node voltage into admittances connected to that point B are 1 by RF plus 1 by R1. Adjacent node voltage is here is V0 minus V0 by RF. Here 0, another adjacent node voltage of that VB is 0. 0 by R1 is 0. No need to write here. VB into R1 plus RF by R1 RF is equal to V0 by RF. Therefore, RF is cancelled. Output voltage V0 is equal to VB into 1 plus RF by R1. But virtual ground concept, VA is equal to VB. VA is equal to VB. Therefore, V0 is equal to VA into 1 plus RF by R1. Calculate VA here. Take filter circuit here. Plus minus V in. This one is capacitance. This one is capacitance here. Capacitor reactance XC is equal to 1 by J omega C, 1 by S. S is equal to J omega 1 by SC. Here write 1 by SC. And resistance R here. Here A point A. The voltage at point is A is VA. The voltage at point A is VA. VA is the voltage across R. According to voltage division rule. According to voltage division rule. VA is equal to the total voltage applied to the circuit is V in into the resistance R by sum of these two, R plus 1 by SC. Therefore, VA is equal to V in into R SRC by SRC plus 1. That is equal to S is equal to J omega V in J omega RC by J omega. Here S is equal to J omega RC plus 1. Therefore, VA is equal to V in into J omega is 2 pi F RC by J 2 pi F J 2 pi F RC plus 1. That is equal to VA is equal to V in into 1 by J 2 pi F RC by J 2 pi F here J 2 pi F RC plus 1 by J 2 pi F RC whole. These two are cancelled. Therefore, VA is equal to V in into 1 by 1 plus 1 by J 2 pi FRC. Here F is FRC. We know that VA is equal to Vn, but V0 is equal to VA into 1 plus RF by R1. V0 is equal to VA into 1 plus RF by R1. Here op amp is in non-inverting amplifier configuration. 1 plus RF by R1 is AF, but VA is equal to V in into 1 by 1 plus 1 by J 2 pi F RC. Therefore, V0 by Vn, that is equal to A is equal to 1 by 1 plus 1 by J 2 pi F RC. 2 pi F RC. Define another frequency. FL is equal to 1 by 2 pi RC. Let FL is equal to, therefore, A is equal to V naught by V in is equal to 1 by 1 plus 1 by J F 1 by 2 pi 1 by 2 pi RC is FL. FL. Therefore, A is equal to 1 by 1 minus J into FL by F. FL by F. 1 minus J into FL by F. This is the AF is also there. That is AF term is also there. Here AF term is also present. Mod A is equal to mod V naught by V in is equal to mod AF by mod 1 minus J FL by F. That is equal to mod AF is AF square root of 1 plus FL by F whole square. FL by F whole square. Here 3 conditions are there. First one is F is less than FL. Therefore, mod A is less than AF. Second one is F is equal to FL. Mod A is equal to AF by root 2. Third one, F is greater than FL. Mod A is equal to is approximately equal to AF from this expression only. The frequency response curve is like that. F mod A, the gain is increases up to F is equal to FL. Here the gain is AF. This one is AF by root 2. This one is a stop band. This one is pass band. Pass band. F less than FL. Here in this band, F greater than FL. This is the analysis of Butterworth Highpass filter.